Okay. In this lecture, what we're going to do is discuss different models for incorporating residence time distribution in real reactors. So specifically, we are going to evaluate the segregation model and the maximum mixedness model. Okay, and this is going to be for real reactors. So we have been thinking about ideal reactors, and now we're starting to move on to real reactors. We classify a reactor as ideal. What we are saying is that the contexts are well mixed. However, real reactors don't have this perfect mixing like in ideal reactors. And the degree of mixing is important because it defines the concentration within the reactor, which defines the rate. And the rate defines the reactor performance, or if we're looking at a single reaction or looking at conversion as a performance metric, it defines the conversion. The exception to this is for first order reactions. In this case, the conversion does not depend on concentration. So if you think about our ideal reactors, the CSTR, the PFR, the batch reactor, and if we use a first order rate law and those, these are what the mole balances look like. And concentration dependence, or there is no concentration dependence, and this is due to the way that the mole balances simplify after adding in the rate law. So the exception is going to be a first order reaction. There is no concentration dependence. For all other reaction orders, the conversion or the reactor performance is going to depend on concentration. So think about a second order reaction. The reactor would have concentration dependence, and we can show this very quickly for a CSTR. The CSTR mole balance is V equals FA naught X over minus RA. If the reaction is first order, then the reaction would be K times Ca. Let's assume it's a liquid phase reaction so that there's no change in the volume. There's no change in the volumetric flow rate. Then the rate would be K times Ca naught minus 1 minus X. And so if I put this, if I substitute this back into the formula, I would get K Ca naught 1 minus X. And what I can do is say that FA naught FA naught is equal to Ca naught V naught. So the concentration times the volumetric flow rate. So that's going to give me Ca naught X V naught over K Ca naught 1 minus X. And so my concentration dependence cancels out, and I could do that for all of my reactors and show that for a first order reaction there is no concentration dependence, or at least there is concentration dependence. It depends, of course, on the fraction of initial concentration that remains. That's the X and the 1 minus X terms, but does not depend on the overall concentration. Now if I took instead a second order reaction, and again we'll say liquid phase for the sake of simplicity. Now I have something that looks like this. If I set this back into my rate law, now I get rid of that, but I only get rid of one of those. Sorry. So I have the second order rate law depends then on the initial concentration. So first order reactions do not depend on the initial concentration, only the amount that's been reacted away, and that's the conversion. All other reaction orders depend on whatever the initial concentration is. Okay, that's a long explanation to kind of get through that. Okay, so we've been talking about ideal reactors. In general, real reactors are not well mixed. And hence, when we have reactions that are something other than first order, we need some way to know the concentration over the entire volume of fluid. So in an ideal reactor, we know this because it's, the concentration over the volume of fluid is uniform. In a real reactor, it's not. We've got gradients. And ideally what we would have is maybe a function where we would know concentration as a function of spatial position. So some function of concentration is a function of x, y, and z coordinates. But unfortunately, we can't get that. That's asking too much. So instead, we use models to tell us this. The models that have been developed to determine the differences in concentration or the degree of mixing, they differ in how they treat mixing amongst molecules from different ages. So basically, we're going to think about all of the molecules in the reactor, and we're going to assign them an age associated with how long they've been in the reactor. And again, this is a model. So in mixing, the age means the amount of time that a molecule has been inside the reactor. And so what we're going to do is group together molecules that have been in the reactor the same amount of time. So molecules within the reactor that are the same age. So these groups of molecules of the same age, we're going to call them globules. So what does a globule look like? So at the very simplest level, it's just some sphere of fluid. So we have different globules. Maybe if we were going to kind of peer into this, we'd see some molecules floating around in here. That's what's going on in there. These are not very well drawn. But basically, this globule is a collection of molecules. I've drawn these boundaries here, so I've kind of encapsulated them. That there is no true boundary. It's a theoretical boundary, basically saying that if I was to kind of fill this in, this is a liquid phase reaction, and if I fill this in so the liquid is filling up all the space, then I have these regions here where I have molecules of some age here, I have molecules of some age here, I have molecules of some age here, but all of the molecules are of, all the globules are of different ages, whereas all the globules are different ages, whereas all the globules contain molecules of different ages, although the molecules within each globule are the same age, if that makes sense. So this is this is a group of molecules all the same age, group of molecules all the same age, but different than the first one, etc. And again, this is just a theoretical model where we are trying to fill a volume of liquid and think about what the concentration dependence is as a function of position within the liquid, and this allows us to do that. So each globule contains molecules of the same age. But all globules are different ages. So if we had globules within a reactor, what might this look like? Basically here I am trying to determine, I'm drawing this very poorly. It wouldn't necessarily be this organized. Basically what I'm trying to do here is determine or come up with a model that gives the spatial distribution of concentrations within a reactor. So I have this model. It looks a bunch of globules, looks like this. Okay, so there's a variety of ways that we can model the way that all of these globules mix together. So here we have unmixed globules. At some point, these globules are going to mix. So when they mix, now I basically have very poorly colored. Basically, they all mix together. We have different models for determining when globules of different ages mix. The ones that we're going to focus on are the segregation model and the maximum mixedness model. These two models differ with respect to when they allow mixing of the globules. In the segregation model, the globules do not mix with other globules until they exit the reactor. Whereas with the maximum mixedness model, the globules mix with other globules as soon as they enter the reactor. So in the maximum mixedness model, the fluid is completely mixed at the molecular level. So that's the maximum mixedness model, looks something like this. The segregation model looks something like this. Okay. So these models, based on their different mixing, are going to give different estimations of performance. For single reactions with orders greater than 1 or less than 0, the segregation model will predict the highest conversion. For reactions that have orders between 0 and 1, the maximum mixedness model will predict the highest conversion. And since first order reactions do not depend on the initial concentration, both models will predict the same conversion for a first order reaction. So for reactions with orders of 1, both models predict same conversion. Okay, so what do these look like? And again, this is not a real system, it's a model. So this is a segregation model and a CSTR. What we see here is we have globules entering the reactor. This is not the way it really happens, right? So in reality, you have a bunch of molecules entering the reactor, and as we showed, so we'll say this is model. We'll say reality. You can go over here and draw reality. We drew this the other day, right? We have our CSTR. Some amount of fluid we have, and we have molecules coming in. Oops, I drew that poorly. Some go right to the exit, and others spend a while in the reactor, right? Something like this. The way we're going to model that is say that the different molecules actually enter the reactor based on their residence time. That's, of course, not what's actually happening. It's just the way that we're going to model it, because that is a lot easier to track and to model than it is to try and track individual molecules happening in reality. So in this model, here we have our globules, or I guess in this picture, these are our globules. Each globule comprises molecules of the same age. But each globule represents a different age of molecule. And then what we see here is that all globules mix as they exit the reactor. In a PFR, we're going to look at this kind of similarly. So we have our globules enter the reactor, similar to in the CSTR case. But then what we're going to say is that they leave at different times according to their residence time. And then they all mix right before exiting the reactor. And of course, this is a model. This is not what really is happening. What's really happening, like we showed here, everything all the molecules are entering, they're just taking different paths through the reactor, and henceforth they have different residence times. We are going to model that as if everything enters and then exits the reactor according to its residence time. So what we see here, globules exit in quotes because they're not really exiting in side streams, they're exiting in reality altogether, but we're going to model it as if they are exiting the reactor at different points. Based on their unique residence time. So both of these give rise to a residence time distribution. Might look something like this here. Okay, so more on these two models. So let's go back to the segregation model. So the segregation model here. There is no mixing or flow between the globules. So the globules are completely segregated from each other. What this means is that each globule can be modeled like a little batch reactor. So we have our globule. You can imagine it's well mixed, but there's no flow in, no flow out, just a bunch of molecules in there. So that's like a little batch reactor. If we want to then calculate the mean conversion over all the globules, what we're going to do is take the mean conversion of globules spending between time equals t and t plus delta t in the reactor. This is going to be the conversion achieved in a globule spending time t in the reactor times the fraction of globules that spend between time t and t plus delta t in the reactor. Okay, that's a lot of words. Mathematically, what that looks like is I'm going to have my mean residence time is equal to x of t times e of t dt, where e of t is my residence time distribution. I can then rearrange this into a mole balance to get this expression. And if I integrate that, I get my average conversion is going to be the sum from 0 to infinity of x of t, e of t, dt. X of t is determined from the batch reactor mole balance. We use the batch reactor mole balance here regardless of what reactor we are actually modeling, because this particular function here, x of t, is not for the reactor, it is for our globule, this. The overall conversion in the reactor is given by this, so it doesn't matter what reactor we use. We can calculate the average conversion based on the batch reactor mole balance for the reaction and the residence time distribution of the reactor. Okay, so we know what the batch reactor mole balance is. So the batch reactor mole balance is going to be dx dt is equal to what? Minus RAV over NA naught. So that tells us, if we have the rate law, And also the residence time distribution, E of t, which for a real reactor we probably have tabulated data, we can find the mean conversion. Okay, so that is the segregation model. In the maximum mixedness model, molecules mix as soon as they enter the reactor. So if we look what that might look like in a CSTR, so here's our, why this is jumping all over the place. Here's our globules, so globules, the reactor, and then our instantly well mixed. But this is, so this maybe, so this is, I guess this is indicating that they're well mixed within the reactor. This is different than a CSTR though. So this looks like a CSTR. Well, what's the difference? The difference is that all of these molecules have different residence times. In a CSTR, all of the molecules have different residence times also, but the distribution is commensurate, or as the distribution is equal to that of an ideal CSTR. In this model, the molecules are coming in at whatever the residence time distribution of the reactor is. So we'll say, but different than an ideal CSTR comes in at a residence time distribution than ideal CSTR. And in fact, it's just going to come in at whatever residence time distribution that is characteristic of that reactor. Similarly, in a PFR, we have our globules entering the reactor, and what we're going to do is model they enter based on their residence time. This is, of course, not what's really going on in a tubular reactor. All of the molecules are entering in the feed, and just some have, in a real PFR, some are going to have, there's going to be a distribution of residence times. The way we're modeling this is that they come in based on their residence time, which again is a distribution. Okay, so just like with the segregation model, we want to be able to calculate the mean conversion for the maximum mixedness model. It involves a lot of math that I'm going to skip. This is going to be one of those cases where I'm going to give you an equation and just say, let's use it. However, if you are interested in the math, click this link. It should take you to where that is derived in the Fogler textbook. Basically, along the course of doing this math, we define a new variable, lambda. Lambda is the time it takes a molecule to move to the end of the reactor. So consider where it enters the reactor and then how long does it take to exit. We then do a mole balance on some species A, for example, in the reactor, and we arrive at this expression, which we can use to get the mean conversion. In this conversion, there are two more variables. One is z, which is the difference between the longest time measured in the residence time distribution curve, and which we call t. So this t bar, capital T bar, is the longest time measured in the residence time distribution curve. And we'll show how to obtain these values based on residence time distribution data in the next lecture.